All right. So this point, yeah, it's part dot 10. We're going to actually kind of look at these structures a little bit more. Look at the sigma and the pi bonds, okay? I think we looked at this before. Okay, this would be this structure, C2H4, okay? And we've been talking a lot about if you have a Lewis structure, you can actually understand the hybridization, for instance, around each of those carbon atoms. It's very symmetrical. It's got 3 sigma bonds, no lone pair electrons, so it's sp2 orbital hybridization. Trigonal planar, 120-degree angle. So we're going to kind of look closer at that molecule. We talked about bond lengths. Picometers is a good way to measure bond lengths. And we talked about the larger the atoms, like the carbon atoms are larger, okay? You would expect the bond between those two to be longer than the bonds between the carbon and the hydrogens, but it's a little bit confounded because actually that's a double bond. You know, carbon double bond carbon has got to be shorter than carbon single bond carbon, which I don't have to show you here. But just to kind of get a sense for that, you see the 120-degree bond angle. Okay, so the carbon atoms have undergone sp2 orbital hybridization. Okay, so shown here is the purple things are the 3 hybridized orbitals, the purple things. The red and blue thing, honestly, are the unhybridized p orbitals, because remember, p orbitals have that dumbbell shaped, okay, around a carbon atom, around that carbon atom, this carbon atom, okay. So the purple ones are getting ready to be sigma bonded to the other carbon and to the 2 hydrogens, and the pi bonds are not are going to the p orbitals are going to be where the pi bond is. Okay, so for C2, H4, it looks like this, where the, I know in some of your homework already it's talked about overlap. Okay, so can you see the kind of shaking hands right there, the overlap between the 2 carbon atoms, the hybridized orbitals, the sp2 hybridized orbitals? We see overlap here and overlap here, okay? And these actually, okay, I have another picture to show you what's going to happen there. Okay, so the unhybridized p orbitals, atomic orbitals of those 2 carbon atoms kind of extend up and out of the plane. And that is actually where just a pair, I know it seems like there should be more going on than just a pair, but in these regions are just where a pair of electrons are to create that 1 pi bond. In like this. Okay, and there it is, the pi bonding, the pi orbitals kind of sandwiching the other thing.
Kind of looks like a burger.
So here again, the pink orbitals are the 3 hybridized orbitals of one of these carbon atoms, and then you have the unhybridized p orbitals sticking out. I have some redundancy here, okay. Some great captions. Makes you hungry, Cameron? Looks like there's eyeballs there or something. Now let's check out these videos. Again, talking about the same molecule. Okay, and then this is actually them together. So we'll see. All right. So just another look at the same molecule, kind of in a different way. Okay. Then we also looked at bond strengths. And so we have some bond strengths in energy, kilocalories per mole, that you would need to break that bond. So for instance, the 108 there is associated with that the sigma bond, the primary bond between the 2 carbon atoms, 108 kilocalories per mole of breaking that particular bond. Now this is not this molecule. You see where it's broken, this is kind of diverting a little bit. The R and the R prime in organic chemistry just simply means there's something else over there. And what we're focusing on here is an alkene bond between, basically a double bond between two carbons. So that's 108 kilocalories per mole versus 65 kilocalories per mole. Now this is where I think we've already said that the sigma bond is stronger than the pi bond, and there you go. The bond to break between carbon and another methyl group out here, carbon that's also then singly bonded to 3 hydrogens, 100 kilocalories. Okay, 110 kilocalories for that sigma bond between that carbon and that hydrogen. Okay, again, still looking at the same molecule. All right, now switching it up a little bit, looking at this molecule. So we could choose either one of those carbons, and we could say the number of sigma bonds extending from the carbon is 2. So it's sp orbital hybridized, so the bond angle is 180. It's what we say linear around those carbon atoms. So let's kind of look at what those orbitals look like. First off, the bond angle is 180. That's what we thought. We talked about bond lengths in terms of picometers. Another way to say how long a bond length is in terms of angstroms. That's what the A above the little, the A with a little circle above it, that's angstroms. Now, one of the things we said about triple bonds is that they are shorter than double bonds, and double bonds are shorter than single bonds. That's assuming they're connecting the same atoms. Here we have this triple bond compared to this actually single bond. So kind of comparing apples and oranges. All right, so carbon triple bond carbon, what does it look like? Well, we said that the carbon atoms have undergone sp orbital hybridization. So this, I wish that they had stuck with the kind of the purple, the convention they had before with their figures. So the way you look at this is, let's see, what color will show up? This one and this one, actually, those are your hybridized orbitals participating in sigma bonds, in one case with the other carbon, in one case with the hydrogen. Up here, and here's where I wish, I just don't understand, I wish they had made one of these, and it could have been this one, I think, red, okay? Basically, those are your unhybridized p orbitals getting ready to make your 2 pi bonds. And of course, the other carbon's done the same thing. So here we go. Carbon, sigma, carbon, and then we have 2 pi bonds. And they definitely have to take the region outside of the sigma bond. So there you go. That's how that one looks like. That one looks really funny. Okay. So one of the things about hybridized orbitals, in this case sp, is that it takes on the characteristics of the things that went into its hybridization, its parents basically. So we have 1 part s and 1 part p, so it's a little more of a sphere than the sp2. All right. So there it is, hybridized, getting ready to bond in this particular situation, and there it is bonded. Kind of a busy sort of diagram.
There's a lot going on.
There's a lot going on. It's good you can see the overlap, and you can see the unhybridized p orbitals, and then the pi bond, and then one more figure down here. Oops, I guess not. And that's it. Okay. So instead of like going through and maybe halfway getting through the part 5 we need to do, that's it for today. Okay?
Oh.
I know, really? Happy Thanksgiving. So we'll finish part 5 and start in on gases on part 8. I think there is assignment at the end of part 5. But